All right. So, if yesterday was the crawl day on reinforcement learning algorithms, today is walking. By tomorrow, you'll be running. By the end of the week, you'll be doing it. So, it's a quarter system, you got to move. This is the equation we went over yesterday. And it's on you if you want to go and there's some more examples. You can redo the ones we did in class. There are some other ones. Um, my attitude's different about this material because the homework is less closely tied to the questions I ask on the test in most cases. But it won't hurt you to do the homework, and it's what you have to be sure that you're actually grasping it and not just kind of nodding through it. Okay, so let's just to finish off what we did yesterday. We took that equation that estimates utility, and yeah, a bunch of here's the things you can play with. Let's say what we would have to do to turn that into a an algorithm we could run, which I've done. I did it with track many years ago. Um, and how would you do that? Okay, well, you're going to have to estimate utility for each action in each situation, okay, which could be a lot or not. It depends on the game, right? Now, if it's the N-arm bandit problem, there's one situation, three actions. That's not intimidating. If you're talking about a chessboard, how many situations are there? Some big exponentialized number, nothing friendly. Okay. And a good number of actions besides. All right. So again, just to kind of remind you of the game that we introduced at the beginning of the unit here, the if you always just take the action with the highest utility, suboptimal behavior can occur. And that should be obvious right from just the n-arm bandit problem, right? If everyone starts with an expected value normalized to zero, and the first arm that gets a hit is better than the other ones, you will never try another arm after that. Okay, that should be obvious that that could be suboptimal. All right. Right, one strategy, it's not the only one, but it's the easiest and it is commonly used. So one strategy is to choose an action randomly. Again, we mean uniformly, a fraction epsilon of the time. You've already seen this name. This is called epsilon greedy. And so this becomes our algorithm, right? So here we are, we're in a situation. This isn't n-arm bandit anymore. We could have, a range of situations. We figure out what actions are possible in this state, A1 through AN, generate a random float. If it's less than epsilon, pick uniformly off out of that list to make sure we're exploring enough. And if not, we're going to exploit by just taking the action which is currently believed to be best in that situation based on our data and our estimates. Okay. And that's what I did with track. It's totally doable. Now, but people don't actually do this. And the reason is because this behavior doesn't scale super well for long runs, right? So this assumes, back to our equation here, that you remember every time you tried an action and you remember every reward that came after and use that in this equation. Okay, that's usually more than what most people want to do. Okay. So today we're going to head for algorithm number two, which is still not quite, okay, no neural net yet. I'm glad to leave the neural net on the side because I don't find that it sheds any light on things. Let's make sure we understand all the pieces first, and then the neural net goes in tomorrow. Okay? All right. All right, so differences in what I just said from traditional reinforcement learning, which we're coming to, okay? In traditional reinforcement learning, the Q values are estimated much more approximately. Okay? Apparently well enough because it's been unsuccessful for all kinds of applications, but more approximately. And then for settings with large numbers of situations and actions, that would be a lot of QAS values that you'd have to estimate. So you might be thinking about, okay, how could I avoid explicitly estimating all of those? So you're looking at some kind of a implicit or explicit compression technique. Okay, and neural nets actually fill the bill there, right? If you have a neural net, you can be on some horrible space with zillions of possible inputs, zillion possible outputs, assuming you have multiple outputs, right? But as soon as you start training it on a couple of data points, it knows more than nothing, and it will give you an answer off that entire input space, right? So that is, in a way, a huge compressor, and we'll talk more about that in a minute. Well, end of this lecture or beginning of tomorrow's lecture. Okay. All right. Again, I okay, feel like I'm looping around here, but I think that's a good thing because there's enough going on that it gets confusing for students. Okay. So is it obvious based on the equations that I gave you that all actions that have occurred before a reward are going to claim some credit for that award? Now, the weighting is going to be different because it depends on the time and it goes in the exponent. So the weighting is going to be hugely different. But all actions that have occurred are going to claim some credit. Now, because of the exponential weighting, what's going to happen is the only actions that get a really substantial impact from receiving a reward are the ones that occurred closer in time to that reward. Yeah? Okay. And again, if actions occur systematically more often before rewards, then they're going to get incremented. Those are going to be the ones with the high expected reward value. Okay. And that is our hope for getting away from what is called very appropriately, I think, superstitious behavior in a reinforcement learning system where, it tries an action, but the action really doesn't have any meaningful impact, but by luck, it then gets rewarded. Okay. And it makes the initial connection. Oh, that action's good. Okay. So that's a superstitious that's a pretty close analog, I think, to human superstitious thought. And you would worry that, well, then how do you ever get after a bad start like that? How do you ever escape? Well, you escape because of this. Because if there's no causal connection between that action and the reward, then it will not be repeatable. Okay. In the meantime, actions that actually do have a causal connection to rewards, things will be repeatable and they will keep incrementing their expected reward values where the superstitious one will not. And hopefully, eventually, that superstitious behavior damps out. It's not always instant. We'll look at some examples today. And if you've got a good eye, you may see that just kind of happenstance impacts the solutions to these systems for quite a long time. Okay, it can happen like that. Any questions on this? Hopefully this is good. Well, eventually I'll stop beating the dead horse, but we're still learning it. Okay, so this is the algorithm for today. Okay, it uses a table instead of a neural net to store the Q values. That's the big difference between what's normally called Q learning in the AI literature. Okay, but some people have used tables. I've seen other professors do it. Someone did it on the project I'm working on right now for ONR. So I know it's not crazy. And again, because the neural net, again, it just muddies the water in terms of what's going on. When a neural net gives a funny answer, there's no real easy audit trail to say. I mean, you can look at all the examples you gave it. Sure, that's what caused the behavior, but how exactly? It's a complex system in my mind, and it's just not that helpful. And it's satisfying answers are really hard to come by. Okay, so here we're just going to have a table. A table is just like a table in Excel. Okay, much more auditable. And what we're going to see is we're going to update the values in the table. So those are going to be expected rewards, okay, Q values. They're going to be updated incrementally based on this thing called the Bellman equation, which you're going to learn today. Has anyone heard of the Bellman equation before? So if you had a control theory course, that would be something that MECE or an EE might take as an undergraduate. You might have seen that in the end of the course. It's more an advanced technique for an undergrad. Okay, so let's talk about this Bellman equation thing and get that out of the way right off. And then we can get to more fun stuff, like actually seeing how the algorithm works. Okay. So, all right, I'll take this step by step so I don't get confused and you keep me honest. Okay. So let's assume that we have some representation of our Q function. Okay. And we're currently in state S1, whatever that is, just to give it a name. S1 is our current state. And however we did it, we decided A1 is going to be our action. It might have been random, it might have been epsilon greedy, and this is just a uniform distributed random variable telling us, okay, it's your turn to try that action, or maybe A1 is the best, given what we have at this point. We don't know, and it doesn't matter. But we've decided it's going to be A1 this time. Okay, so we take A1, and as a consequence, we receive a reward, lowercase r, immediately. Okay, and as a consequence of taking the action, it's changed the state. Normally, the state does change in response to actions, not always, but normally. Okay, so it's now state S2. Okay, everyone with me? That's our little scenario. Let's see if we can drill in and understand it and reason our way to the Bellman equation. Okay, so okay, I'm now in S2. Tell me, what action should I pick now?
A1.
I just did A1.
Why can't you do it again? We received the reward.
Okay, we received the reward. Okay, but okay, a little catch is that the reward R could be negative.
Oh.
I'm not saying what it is. Right, and in which case it's basically a punishment, not a reward. So maybe you don't want to take A1, maybe anything else except A1, but we just don't know.
Right.
A2 to try something different. Try something different. Okay, any other kind of thing. Those aren't crazy, but I think we can do better. Let's assume we're going to be in exploit mode. We want to exploit this knowledge that we have. I'm assuming we know this function, right? That's pretty powerful. Anyone like to suggest to me how I can use that function to pick an action? You thought you were following my slides before now, right? You weren't really. Okay, here's how we're going to do it. We're going to take, we have this function. We know we're in this state. So we're going to look and we're going to let S be S2, okay? And we're going to figure out what actions, so that not mentioned here, but presumably that's not a hard thing. We got an action list of possible actions. We're going to go through that list one at a time. We're going to evaluate Q of that action, S2, and look at the number. And then what? What do we do when we're done?
You would theoretically pick highest.
Take the highest. That's what we do in exploit mode, right? And that's the rational thing to do. That's based on our best information. That action, whatever it is going to be the best. Okay? Is everyone tracking now? All right. What do we have? Okay, how can we write the best return for that action? That puts this something a little bit like a trick question. It's not meant to be. What I mean is that let's see. So we have Q, right? We were just looking at Q for various actions, okay, in state S2. Yes.
And I might miss this. Is there any relationship between, say, A1 and S1 besides the fact they're both the first in their sequence? Like, is there any association that we think that doing A1 in state 1 is beneficial, or they just happen to both be the first action?
We don't know, because remember the way the epsilon greedy works, we could have just been told, you will pick a random action this time to make sure you're playing the entire field. Okay, so we just don't know. Okay, so what we want is the max. This would be the way to write our expected return. Right? Whatever that action is, right? Have you seen notation like this before? It's just new.
I mean, we've seen math.max stuff going before, but
okay.
It's not a week to figure out what we're doing.
Okay, all right.
All right,
so that is
means the maximum the A value that maximizes that expression.
Okay, it's not the A value. This, as I wrote it, is the max itself. Now to get to the A, that is where I want to go. then we say argmax. Argmax is the A value that maximizes this expression. Okay, so the expected return, just the answer to the question, that's this. Okay, but I think argmax is going to be where we want to go. All right, well, let's see. All right, so this is the real hard. Here's the $1 million question here. So if our Q function is correct, if it's absolutely correct, which, I mean, you know, we're learning this thing, so it's like never going to ever be absolutely correct. But let's assume it's absolutely correct. I mean, if we're in a good run, where we're very close to the end of the run, it should be very close to correct. And on a small problem anyway, maybe not on a big full-scale problem. Okay. All right. So in particular, how does this? So this is our estimate of the expected reward we're going to get if we take A1 action A1 in state S1. Okay. Now the value over here, okay, is the expected return. We're taking the best action in S2. Now those should be related, right? I mean, this is all part of the same flow. We were just there in S1, we had that estimate. Now we're over here and we have this estimate. Those should be related, right? Now, how are they? How are they? This is what we have. Q of A1 in S2. Do they be identical?
Well, is it Q of A1 S2 or the board's
Oh, no,
or is it Q of A1 S1?
Okay. Better? How are those related?
This is probably a dumb question, but we already know that Q of A1 S1 equals S2, don't we? But we did.
No, we don't. No, we don't.
We
This is
got
an
it.
expected return. S2 is a state.
One. Oh, we got all.
Yeah. Okay. Yeah, R needs to come into this picture too. Right? So this was an estimate of the entire future reward, right? With discountings by lambda or gamma. It's written both ways sometimes. So we've been writing lambda. I'll write lambda. I don't say that's not gamma, but okay. Okay. So we were anticipating a certain reward. Well, how does R relate to that reward we were anticipating?
If it's perfect, it should be. They should be the
Max R. Okay. Not equal, right? Because that assumes we're not going to get any reward after that R if it's equal. I'm hoping to get more reward than just the R. Happy to have the R, but then I'm going to have more, right? So this should be R plus something.
Plus the Q of all the future states and best actions.
Okay, plus the Q in the next state. So this already is supposed to wrap everything up from this state on moving forward in the simulation. Okay, now the only thing that we're missing here is it's going to have to involve both of those. It's my immediate reward plus the additional reward I expect to get. Okay, the only thing we're missing is that there's going to be a discount factor here because one increment of time goes by. When I took action A1, I received the reward, some time went by. So all this stuff coming up in the future all needs to be discounted by that one time step. Okay? Kind of put us all in the same time frame as this guy. Yeah, that would take some thinking about. Isn't that an obvious equation? This was kind of a big advance in control theory when Bellman figured this out, and it's been leveraged in all kinds of ways.
I'm gonna be honest with the entire equation. The lambda is the one that makes the most sense.
What do you?
The rest of it, took some thought. The lambda, I'm like, oh yeah, that checks out.
Okay. All right.
Good.
But are there any questions about this?
So
Yeah, go ahead.
So the Q part of the equation is essentially like recursive because, am I understanding this correctly? So Q A S2 would then be R plus lambda max Q A S3.
You could write it that
So
way.
on and so forth.
You could do that in non-capital, yeah. And in some cases, you might want to, if you go theory. We're not going to need to go that far. Okay, now, So that is the Bellman equation. Right. Okay. So without that, there wouldn't be reinforcement learning, basically, because this was all the early versions used of Bellman. Okay, so all right. Here, it's gamma instead of lambda. Same picture. Gamma is the other name people often give to the discount factor. All right, good. Yeah,
Did we ever answer what action we wanted to pick?
yeah. The
I'm sorry, I probably lost.
the one that makes this
Okay.
the larger, right? In other words, the one that has this as its expected return.
Okay, so I understood in that abstract sense of pick the best one, but not that, you know, there was no answer like, oh, it's A7.
Yeah, no,
Got
this is math, okay,
Yeah.
right? We're doing this totally in general. We have no way we have nothing to grab onto other than these variable names. All right. Okay, so that's the way it's supposed to work. Okay, so think about it. It should make sense. If it's not making sense this morning, I guess that's fine because it's not a trivial thing, but keep looking at it till it makes some sense to you. And now we need to use it, right? Because of all real Q learning, well, these are all pretty much uses the Bellman equation. All right. So the Bellman equation, though, you'll notice it's not an update equation, it's not an algorithm, right? What we need is we want to be able to actually estimate Q from our experience in our simulated world, taking actions, seeing states go by, receiving rewards. Okay, so we still have more work to do. All right. This is it. If you get to the bottom here and understand it, I think this is the heavy lift, the end of the heavy lift. Okay. So, right, if Q, remember I said if Q was perfect, right? Well, Q's never going to be perfect, and particularly not when we're starting off learning and stuff. So in general, it's not going to be well. Okay. The question is, okay, it's not equal. It should be equal if our Q was correct. If our Q was correct and consistent, it should be equal, but it's not. So what should we do about that? The answer is adjust Q in some way, right? Clearly. Well, let's try to make it consistent if it isn't consistent. Okay, but adjust it in what way? Okay. If we were sure that the reason it's not equal is because this was garbage, but this is perfect. Right? Then I would know what to do. Right? I would just take this value, right? Again, so I haven't really been emphasizing it. Where this is going to be represented by a table. It's a two-dimensional table, right? Actions one way, states the other one. I could go find this entry and just get rid of the old value and replace it with this perfect value, if it was perfect. But it's using the same bad function, that we have issues with. Okay. What is generally true, okay, is not that this is perfect and that's not. No. But this is better than that. Because it's based on a little bit more actual experience of the world. Just one step's worth. But that's enough. That's a big enough lever to let us improve Q incrementally all the way up to the great results that have been gotten with reinforcement learning. Now, right? In particular, this value is something concrete that we came to work. Even if that value is a 0, we still learned something, okay, about taking actions in this state. But this is the better estimate. So what we're going to do is use this to improve this. We're not just going to accept this as the new value of this. That would be going too far. But we're going to nudge this in the direction of the right-hand side of the equation. That make sense? Okay. All right. And that is what this equation at the bottom is saying. What it's saying is, hey, what you're going to do is, after you go through that experience we just had, is you're going to update Q of A1, S1. And how are you going to update it? With one of these exponential averaging processes here. You're going to have alpha is going to be a small number, right? Small positive number. And notice the 1 minus alpha versus the alpha, right? We're going to take a little fraction alpha of the old value of this and throw it out with the negative sign. And we're going to replace it with an alpha amount of the better value, supposedly better value. Make sense?
It's actually the same structure as you were talking about when we were talking about.
Yeah, well, this, you see this again and again in fishing. In different contexts, yeah, so if you get comfortable with it, it really pays dividends for you, because yeah, after a while, you should be able to look at this and say, I know what that is, it's just another exponential average. Like I've seen a million times before. Okay, so that is the way we're gonna update our Q table. And that really is it. Okay, now you need to really understand this, though. At least, I mean, we can start, even if you don't understand why the Bellman equation is true, as you're sitting there right this morning, and you want to think about that some more, I don't blame you. But just as an algorithm, we can go by rote and just follow it through and make sure we understand mechanically what it does. We'll need to know it for the test. So, speaking of which, we are getting to the end of where I'm going to draw a line. The next test. So I probably should have the test. I would think like next week. I mean, we'll finish the material this week. So I'll assign you a new lab on Friday. You have the other lab due Monday. So maybe like toward the middle or end of next week. I mean, you guys, I don't know how well you know your schedule, but you may have other exams or whatever. We need to pick a day. So I'll just let that hang out there. Maybe tomorrow we can pick a day. Good. All right. All right, but for now, to make sure we understand this, let's do an example. Okay, so this is a computational example. There are a couple of these, and you need to spend time with both of them. Okay. Come on. Really? All right, oh, it's opening it every time. It's just not popping it to the front. Thanks very much. Okay. All right, here we go. So this is actually pathfinding, which is one of the one of the early demo problems people use for reinforcement learning, even though it's not particularly sensible. We know how to do pathfinding well. You're going to use systematic search to do that, not reinforcement learning, but to learn the algorithm, it's perfectly good. At least you understand what the domain is. Okay, so let's shrink this down. That's so small. All right. I'll scroll a little bit. Let's read the top, and then I'll change it and scroll it around. Okay, so right. The black state's the goal state. Okay. White state's the starting state. Okay. You get a reward of 1,000 when you find the goal state, when you step onto the goal state. You get a penalty of negative 1,000 for attempting to move off the map. Got an electrified wire. So that's bad. We're trying to move off the map. All right. Rewards are considered to arrive immediately after the action. Okay. In other words, they're undiscounted. So you'd be thinking, oh, he means don't apply lambda or gamma or discount factor to the reward when it comes in. You take it just as it is. All right, a random action is taken 10% of the time, i.e. an epsilon greedy strategy with an epsilon of 0.1. We're going to use a discount factor of 0.9. That's our gamma or alpha, what we want to call it. Okay, and the learning rate, that's our alpha from the last slide, is 0.1. Okay, or exponential averaging of our Q values. And the mover is going to teleport to the starting, i.e. the white location, after reaching the goal. And yeah, you can, there's some tools here for messing around with this stuff. Okay, let's take a look. Let's start reading this, and then I'll shrink things down. This is the start of our Q table over here. We'll look at that in a second. This shows the start state and the goal state and how many steps we've already tried, the last location we were in, the last action we've tried, the mode, explore, exploit, okay, and any reward that we just got. Okay, so track things. And the level at which I expect you to understand this algorithm is literally that you should be not surprised by anything it does. You should totally understand it, in particular, what it's doing with the Q table. Okay. Again, I'm going to shrink it down so we can actually see the Q table, or actually maybe just if I scroll up. Yeah, that's all right. That's pretty good. All right. Sorry about that. I don't mean. Sorry. Okay. What? Move. Yes. Okay. Fantastic. Okay, let's see if this looks like a Q table to you. Here are the states, A through I. See them up there? Okay, that should look okay. Here are the actions, northeast, southwest. That should make sense. Okay, for each one of these, this is the expected. If I'm in state D and I go south, it says the expected long-term reward is 0. Okay, good. You see how to read it. Okay, you saw the equation we're trying to use for the update. Just telegraph it so I can follow it as well as you that. Delta of Q is at Q of A1 S1 comes 1 minus alpha Q of A1 S1 plus alpha times this. Okay. Let's see if we can do it. All right. So let's hit the step button. Boom. Okay. Easiest problem, easiest learning problem ever. All right. Well, let's see what happens. It's all good learning at this point. Okay. So what just happened? We started off in step H, right? We're currently in step I. Okay. Which value on the table did you expect to change? The one from where we came from, right? Q of A1 S1, before we took the action. That's the entry in the table that changes, not the one for the new state, the old one. Okay. And we were in state H. Okay. And which of these changes? Well, only the one where we actually took the action, because that's the one we get information about. That's this. Okay. Now, does it actually follow the equation? All right, let's see. The old value was what before we started? 0. It was 0. Get about this term. This alpha is 0.1. Okay. Lambda is 0.9. Okay. The reward set 1,000 when we get to the solution, which we just did. Okay. So 0.1 times 1,000, that's 100. Okay. Plus this, the best we expect to get in the new state. Well, what's the best we expect to get in state I?
0.
0. So we can also ignore this. So it's 0.1 times 1,000. It's 100. And that's the increment that we saw. That makes some sense. Okay, let's keep going. It's we'll have to restart it in a bit because this never happens. First of all, it's just random that the solution is right next to the starting point, and we stepped on it the first time. So it's very very strange first example. Well, let's step. Okay, now we teleport back to the beginning, right? No action was taken. Okay, there's some notes about that in the slides, but that should make some sense to you, right? We didn't go back to H because we made some choice. You must go back to the beginning after you finish. Okay. All right. So here we are. Okay, we're in, let's say we have a special mode here, reset mode. Okay, let's step again. Okay, so it is exploit mode. Okay, what exploit mode means is for all the possible actions, we look for the one with the biggest value. Changed already, right? This was 100 a little bit ago. That's clearly bigger than 0. So we would select action east. Okay. All right. Now let's see, Andy.
Read over how that.
Yes, I am. Yeah. While we're warming up on this, I absolutely want to do that. Okay, this is 0.9. Okay, this is the old value from the table, right? This was 100, right? So there's your 90. Okay, and then we have 0.1 times 1,000 over here. Okay, these values in the new state, I, are still all 0. And they're going to stay 0 because once we get to that point, we just teleport back to the beginning. We'll never select an action in state I. So 100, it's 90. 190. We good? Now, eventually, let's see, we reset. Okay, now you can just see how the math is rolling here, right? So now it's going to be 0.9 times 190. So the numbers start to get ugly. Okay, but should still be computable. Okay, I just want to show you that eventually, hopefully, we're going to see an explore step here, and it's going to try somewhere else. Maybe exploit, exploit, exploit. Come on, it's truly random, so I can't make it do it if it doesn't want to do it. Look at this. Okay, in the meantime, you see, now we know what is the true value that belongs here. It's 1,000. Okay. In this case, we would have done better if we would have just accepted the new value. If we would have immediately gotten to a good answer, but that's not normal. That's not normal. Okay. And you see, because we're using exponential averaging, it's going to take a while to average up from 0 all the way up to 1,000. Okay. I'm still looking for my explore step. Oh, an explore step. Hooray. Okay. What did it do? It tried to go south. It tried to go south. And what happened? Hit the electrified wire down there. Okay. Got a reward of negative 1,000, I thought. But that makes me wonder. So why is it negative 38? I don't know. Okay. Let's see. Let's see if we can figure it out. All right. Okay. So our old belief for this was 0, right? We thought going south would give us 0. Never been tried before. Okay. This is going to be negative 1,000 this time. Okay. Maybe here. So the state we end up with is what? We end up with. I think that's the rub. And so it is a kind of a bug. Like we're going back to state H. And so it's now taking the.
You don't actually move, so it's factoring in 686.
Yeah, it shouldn't probably be doing that. You know, I would consider that a bug. So I'm not going to. If you understand what's going on, it thinks that also teleports it back to H, and H is a good state where it sees it can get a good value. So it's not so unhappy to have hit the electrified wire as it should be. Okay. Right, let's start it again.
Would we expect it to be minus 1,000 then?
After a long time.
Yes.
The same way that this is, but it's not going to happen because of this coding it. Yeah.
Yeah.
All right, good.
If you take the hard instead of random start, it lets me know.
Yeah, that's right. We can make it harder, or you can just reload the and try your luck. Okay, that's harder. Okay, and yeah, there are some here where you can. There's an easy case. Here's a hard case. Okay. Well, let's go all the way to a hard case. Sure, why not? After having that really, really easy one. Okay, so let's try again. Get a little more experience here. Okay, step. Okay, it's exploring. It's exploiting. It's just, oh, what happened? Okay, it already, oh, for pity's sake. I'm not really keeping up. So it already tried to go south one time, okay, and the value went to negative 100, and that's here. Oh, wait, no. It tried to go west out of state G and hit the electrified wire. It also tried to go south out of state H and hit the wire. So we have 2 minus 100 values there. Hopefully that makes sense. Okay, so now when we start from G, if we do an exploit, what's it going to pick? Like anything except west, right? It learned west looks worse than the other options. So if it's exploit, okay, it goes east. And now what state, if it's exploit, what's it going to pick out of H? Anything but south, yeah. Okay, but it actually didn't explore. So it could have gone south again, right? Because explore, it doesn't know. It doesn't know that negative 1,000 is reliable. You know, because I told you, but it doesn't know. Okay, so we went back to G. All right, good. So if it's exploit, we're gonna, again, anything except west. So it tried north, tries north. Now you notice the values are not changing here. Does that make sense to you? Like we're in D and we went north. Okay, why are the values not changing? Right? So we have no reward. We have 0 over here for the initial value. And we have the best you can do in the new state is also zero, because we have just zeros across the board. So 0, 0, 0, 0, nothing changed. Okay? All right, let's go. Right. Thought it was gonna get there. All right. Now it's just gonna bop and back. All right, look at that. Got something positive. All right, now this is the way a property of reinforcement learning. Okay. Now I'm about to go back to the original state G. And how much smarter am I going to get when I go back to state G? Not at all from where we were last time. What did I actually learn?
A single state.
From which one?
B.
If I'm in B and you ask me to exploit, what should I do?
East.
I should go east. That's what I learned. So now, so that's very little, right? You start to understand why these things take a while to learn. These are not very fast learners. But now we've actually doubled our the set of states, which will get us a good answer, right? If I, of course, stumbling into C is always great, but now if I just stumble into B, I'm going to do the right thing, probably, if I do an exploit step and go right to C. Okay, so it does represent some learning. Let's start again. Looks like he yeah, he tried to go north from A. So hit the wire. Okay. Ah, I see. So it doesn't. So the way the logic is, oh, that's interesting. No, you just stay where you are when you hit the wire. I didn't realize that. I thought it would reset it. So I think maybe there isn't a bug. Just that the logic wasn't what I figured. You guys, y'all see what's happening, right? It's not resetting when it hits a wire. At least not that. Did it reset before? Okay, I'm going to keep an eye on that. Okay, now we're in state B. Okay, now we're good. As long as we don't get an explorer command now, we're good. We're going to go all the way through to the goal. It's an exploit. We got another 1,000. Look at the B estimate there going up toward what it should be, which is 1,000, right? Okay. We're going to teleport back. All right, in G, we're still not very smart. In E, we've never been in E. Never got any feedback in E. We're in H, we know not to go south. Okay. So here we go. All right. So what just happened here? We tried the other electrified direction. Okay. All right. Great. All right. And now we're in D. We tried to go west. Now we're in A. Notice that I didn't even realize it had happened. From A, we had tried east and we actually learned something. Do you see how the learning kind of diffuses back from the goal? When we went from A, when we tried B, B doesn't have a great value, not as good as C, okay, only 190, but it was enough to actually give it. And when we do an exploit step here, what's it going to pick? I mean, it doesn't matter that this is 9 versus 1,000. It actually should be 1,000, right? Because if you get in step A, you just go east and you get 1,000, right? Or maybe with some discount, okay? But so with 2 discounted steps, right? So, okay, so it should be 810. Should be 810. Okay, that's a far cry from 810, but the behavior is going to be correct. If you go there and you say exploit, it's the best option. So it's going to pick it, right? Okay, so here we go. So as long as I get an exploit, was there a question? Feeling I missed something. Okay, okay, go to B. If it's exploit, we're going to go home. We got it. We teleport back. Okay, still have no idea what to do in G, except we know 2 things not to do. Okay, all right, so we go east, which is okay. We go north into E. We've never learned anything from E. Going to F isn't going to help us. We don't know anything in F. Okay, we learned something bad in F. Don't go east. Okay, we go back west, go back to F. Okay, now it knows not to go east again. And what did it actually do? It went east because it did an explore step. So there you go. That's the double-edged nature of the explore steps. They do make sure you explore stuff, but that means you do the same dumb thing multiple times. All right. It goes back to east, goes up to B. Okay, from B, we know where to go. We're done. Okay, so after a while, so already like from C, B, or A, as long as you stumble into that top row, it knows what to do. B as well. right? Yes, D as well?
Delta. Now,
Oh, it does. Look at that. Correct. Correct. Now D as well. So like almost half the steps. If it does it just if it does exploit, it will solve the path. Okay. And yeah. Okay, we didn't explore from B. Oh, yeah, because and for me, you see, because of that step, now E has a positive value as well. So it joins the club where it starts pointing us in a reasonable direction. Now, what you will not always see is because the corner, actually, there's kind of a downside of having this hard problem in that there isn't really a wrong direction, right? As long as you keep percolating up to the northeast. What you will see sometimes is the solution may be here, but the way you see it, the first time you see it is you went here and then here and then here and then here and then here. Okay? Yeah, go ahead.
if there was a better solution
Yeah,
through HIF,
yeah,
across the bottom and up,
yeah.
I would think, run into a problem where as soon as this thing goes to H, it now goes to E the next time.
Well, this is what I'm saying. Yes, yes. But if it really was better to go via IF, right? Let's say there's no terrain in this, but this was slow go terrain. You'll get there, but it's not the best way, right? Then eventually it should explore over this way and it should realize, oh, there's actually a faster way, right? There's more points to be had going from H to I than going to E because I get to the reward quicker.
At the point we've got I'm sorry, I cut somebody off on my cat there. Okay, never mind. So at the point that it has, worn a pretty deep groove because it's gone over it once or twice.
Yeah,
Then if we're doing a 1 in 20, is it explore, a 1 in 10 is an explore step?
yeah.
1 in 10. So the odds of getting, if we say, okay, hey, I've got a higher incentive to go up to Delta because I've done that a couple more times and they're equally valuable, but I
Mhm.
just happen to hit Delta first. So most times I will chase the Delta. If I get an explore, I'll go over to a hotel. So it would be, in this problem, you're only at 1 in 100.
Yeah.
But as soon as the problem gets more and more complex, the odds of you actually ever hitting redundant explore in the correct direction get tiny.
It can be like that, right? But what you have to realize is if you keep going forever, that will happen. It will happen infinitely many times, and eventually the correct data is going to overwhelm the initial increment.
Can you also modify this to incorporate cost if that was factored in?
Well, that would you could just put that into rewards, maybe. Like I could make. I mean, slow terrain I might make you waste a turn if you walk into a square with slow terrain. And why will that matter? Well, because now when you get to the solution, it will have one extra discount factor applied to it, so it will only be 90% of what you could have gotten if you would have found a way through good terrain. Yeah. So yeah, you can totally do it. Right. All right. So I'm going to stop it there. Fire this thing up and see if you can make some sense of it at home. Look at the Bellman equation. Maybe come in with questions, or maybe they'll come into focus. Hopefully, it comes into focus. But yeah, questions are welcome. And I'll see you guys tomorrow. Yeah.
I won't be here tomorrow. I have a doctor's appointment.
Okay.
I'll be back on Thursday.
Okay. I hope there's normally been videos. It's been well behaved every day. So I hope that's the way it is tomorrow.